Now let's talk about anomalous zeeman effect. And what is anomalous zeeman effect? Is when we apply the magnetic field, and that magnetic field is weak, and what we find is that we find that in the direction perpendicular to the magnetic field. If the magnetic field is horizontal, and and the magnetic field is perpendicular, and what we find in perpendicular direction, each spectral line gets split, and these spectral lines, they get splitted in more than three components, and in the direction of the field, each of the spectral lines is split in more than two components, and this splitting of spectral line on applying the weak magnetic field, weak external magnetic field. Uh, what this is called as anomalous Zeeman effect. So what we have is in perpendicular direction we have more than three components, and in the direction perpendicular parallel to the magnetic field, we have more than two components. And this effect basically finds its explanation in the concept of spin orbit interaction, and that means spin. The concept of spin has to be incorporated in explaining the anomalous Zeeman effect. So talking about the total resultant angular momentum vector. What's that? The total angular momentum vector is the vector sum of L and S, where S is the spin angular momentum, and L is the orbital angular momentum. And what we do is that we have a situation here, like what we have is we have orbital angular momentum, and that orbital angular momentum is L, and what is opposite to this orbital angular momentum is orbital magnetic moment, and that is mu L. And then we have what we have is the spin angular momentum. So choosing this as spin angular momentum S vector, and this S vector will find its spin magnetic moment opposite in direction. Say this is mu S, and we have a vector and we have another vector, and we will have the resultant vector, and this resultant vector is vector J, the total angular momentum. And assuming that this magnetic field that's applied in this case is it is along the z direction. So this is the direction of the applied magnetic field. So what we have a situation, and that situation is like this, and here what we have is bz, and at the same time we will have the component of this j along this z direction, and that is jz. So what's going to happen here is we have L vector, we have L vector, we have S vector, and we have the resultant of these two vectors given by J, and this J precesses uh, along the direction of magnetic field, and the magnetic field direction is chosen here as Z. So we can have this JZ. This JZ will be simply MJ H cross, and this mj is the total magnetic quantum number, and this mj will have 2j plus 1 values, or we can say that the values will range from minus j, then we'll have minus j plus 1, so on and so forth, to minus j. This will be the situation. And So what we have here, we have a situation, and that situation uh, is uh, uh, is self-explanatory as long as the geometry is concerned till now. So what we have is we have this this magnetic moment of this J, which will be opposite to J. That will be mj mu J. Sorry. So what is this mu J? This mu J is it is minus Ge by mj. This equation is already obtained in the previous lectures, where G is Landé G splitting factor, and E is the charge of electron, M is the mass, and J is the total angular momentum. And this G has already been derived in the previous videos. So the value of this G, this Landé G splitting factor is this G is 1 plus J times J plus 1 plus S times S plus 1 minus L times L plus 1 whole divided by 2 times J plus 1. So this is our expression for Landé factor, and this factor has already been this expression is already derived in one of the previous videos where we have discussed the vector model of atom. So proceeding from here, what we can do is we can take the ratio of the magnitude of magnetic moment of J and J vector. So what we are going to get from here is we'll have mu J, its magnitude, divide by yeah J vector magnitude is it is G E by M. All right. Because we cannot have the division of vectors, so we have taken the magnitude of the ratio of the magnetic moment of J and the magnitude of the total angular momentum. Now we have already derived the Larmor's precession formula. So this Larmor precession formula, and what's that? That formula is that this omega is mu J magnitude by J magnitude times B. All right, and we can write this omega is G times this ratio is E by M. So instead of mu J by J, we can write G E by M and B. And this omega is the angular frequency. And what we have is this is our external magnetic field that we have been applying on the system, and we can see that this omega angular frequency, which on simply multiplying by h bar will give us energy, is proportional to the external magnetic field. So we can write down. That the change in energy that we have, that is the dot product of mu J dot B, where mu J is the magnetic moment, total magnetic moment, and B is the external magnetic field that has been applied. And what we have done, the same thing in case of normal zeeman effect, and the result of this thing comes out to be omega Jz. And we would like to write down that result here. So what will be that? That will be this delta E is omega Jz. So this is omega Jz, and for omega, what I have G E by MB, and I'm going to write this. This is G E by M B times B dot Jz. And what is this Jz? This Jz is MJH cross. All right. So we'd like to write down G E by M B MJ. This is not the dot here. This is the plain multiplication because this is evaluated already, and so this is B, then M, J, H cross. And we would like to write down this change in energy in terms of Lorentz units. So this is G. I can write down EH cross by EH cross by M, and okay, times M, J, and B. All right, and so if we choose here in terms of the energy in terms of wave numbers, and in that case what we will use is delta t. So this delta t will be minus delta E by hc. And so there's no difference. The difference is in terms of smallness of energy. So this wave number, the change in wave number, which is represented as delta t here, is minus delta E by hc, and we can write down this minus is deliberately introduced in order to be consistent with the forthcoming equations, where finally the result has to come positive. Now the point here is that I can write down this as minus 1 by 2 pi h c, 2 pi hc. H, it should be h cross here because I want to convert this h into the h cross, and then I will have G, okay, then mj, and then I'll have eh cross by 2m times B. Okay, so I can write down the final thing. Delta t is this is this is gm mj times eb by 4 pi mc. Now this term is what's called as Lorentz unit. So I can write down that this delta t is g, okay, the minus is there, minus g m j L dash, where this L dash is nothing but Lorentz unit, and it is EB by 4 pi MC. Uh, this this is the required expression for the time being, that gives us this shift in wave number of the present situation. So what can I say here is that this for the weak field, I mean, the magnetic interaction energy, of what we have is we have we have the interaction. We have incorporated the spin angular momentum in order to understand the anomalous behavior of anomalous Zeeman effect, and this equation automatically leads to the splitting of lines, and precisely explains the splitting of lines when weak external magnetic field is applied on the system. Now to have the clean understanding of this thing, what should we do is we would like to consider the problem. We'll take an example of what's called as the spectrum of sodium, and the spectrum of sodium has two lines, and we would like to uh, go with that example, and try to have some understanding that how the things happen, to explain the this what's called as anomalous Zeeman effect. Now, what is happening is, if I take an example of the spectrum of the sodium atom, and what we have there, we have D1 line, and this D1 line is obtained due to the transition. It is obtained due to the transition from 3p to 1 by 2 state to 3 to S, not P, S 1 by 2 state. And we have another line there that's called a D2 line, and this line has a transition. This line has a transition from 3p to 3 by 2 to 3s2 1 by 2. Now, on applying the external magnetic field, this S1 by 2 state, it splits into two substates when we go with its multiplicity, corresponding to mj, corresponding to mj equal to minus 1 by 2 and plus 1 by 2. And the P3 by 2 state that we have, this P3 by 2 state, it splits into four substates, and and uh, that can be evaluated from its multiplicity, corresponding to mj as minus 3 by 2, minus 1 by 2, 1 by 2, and plus 3 by 2. So these are the states when you have the transition for P3 by 2 state. So what's happening over here is that this gives the quantum numbers that are necessary for the determination of the splitting, and we have already seen that this change in energy is dependent on, it's dependent on magnetic field, and it's dependent on splitting factor, and it's dependent on magnetic quantum numbers. So suddenly, there's a clear indicator of the fact that there will be splitting. Now, let us get more concise in this problem by choosing to have this conversation in a table-like situation. So let me go with some table here. I'm going to take the state first, then I'll take its L orbital quantum number, then I'll take its spin quantum number, then I'll take its total quantum number, then I'll take its Landé splitting factor, then I'll take its mj, magnetic total magnetic quantum number, and then I'll take mjg. So these should be the indices. So here I would like to have the state, then I'll have L, then I'll have S, then I'll have J, then I'll have Landé splitting factor, then I'll have mj, then I'll have mj. I'll multiply this with Landé splitting factor. So going with the first state is what's that? That is S1 by 2, 2. Going with this state, what we will have here, the orbital quantum number for this is 0. It has a spin of half, so its j is going to be 1 by 2. We cannot take the negative of j, so we cannot take the other part of it. So its Landé splitting factor is going to be 2. Its mj will be 1 by 2 and minus 1 by 2. And on multiply this mj with g will give us 1 and minus 1. Right. Now the next state is our 2p 1 by 2 state. 2p 1 by 2 state. And for this, L is 1, and for this, S is 1 by 2. So J, for this, J is 1 by 2, and for this, G is 2 by 3. And its mj is 1 by 2 and minus 1 by 2, and its mgj will be automatically 1 by 3 comma minus 1 by 3. Then we will have the third state, that is 2p 3 by 2, and for this, L is 1, S is half, and its j is 3 by 2, and its g is 4 by 3, and it has mj as, it must have four values, that is 3 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. And then what we'll have, mjg will give us 2 times 2 by 3, and minus 2 by 3, and minus 2. Right. So So this will be the tableization of the transition, the D1 line and D2 line. Let's go with its spectrum, and let's try to analyze the spectrum here. So what we have the sodium, and for sodium, what we have two lines in absence of external weak magnetic field, D1 line and D2 line. And this when we apply the magnetic field, so what happens is now since this D1 line uh, uh, is obtained corresponding to the transition from 2p1 by 2 to 2s 1 by 2, and according to the selection rule. So what is the selection rule here is delta mj is 0 and plus minus 1. And what we have four transitions are allowed, so that this D1 line it gets splitted into four component lines. And similarly, this D2 line, I should also go with its wavelength. For D1 line, the wavelength is nearly 589.6 nanometers, and for D2 line it is 589 nanometers. and and this D2 line is obtained corresponding to the transition between P 3 by 2 to S 1 by 2, and for which we have eight transitions. There are eight transitions possible for this, but the selection rule, that's delta mj is plus minus 1 and 0. It forbids the two ones, and only six transitions are allowed in this case, and hence we can say that this D2 line is splitted into six uh, components, and delta mj equal to 0 here in this case. It gives rise to the pi components, while delta mj equal to plus minus 1, it gives rise to the sigma components. Gives pi, and this gives sigma components. And we can see here that what we have the splitting of this uh, 2p3 by 2 state, and it splits. The splitting is shown here, and the splitting is shown here for D2 line, and I have not incorporated the splitting for D1 line. So for D1 line, what we have the first thing, uh, the transition should go like this, okay, and the next allowed transition is like this, all right, and the next transition that we can have is this, from minus 1 by 2 to minus 1 by 2, and another will be from plus 1 by 2 to minus 1 by 2, and they'll follow the selection rule. You can check that delta mj for this D1 line, and you can also check the delta mj for this D2 line. And what we finally see here is the splitting, and this splitting is purely explained quantum mechanically, where we have the transitions, and these transitions have been defined here for D2 line, and these transitions are defined here for D1 line. And for D1 line, what we finally obtain in spectrum is we obtain basically we have 4 for D1 line. What we have is sigma, then we have pi, and then we have pi, and then we have sigma. And for this case, for D2 line, what we have sigma, we have pi, and we have sigma, and we have sigma. And this should be a piece of exercise for you, dear students, that you will check all these transitions and see if I have committed some mistake in doing so. If I have committed, I apologize for that. And with this, I would like to say goodbye and good luck to all of you.